So we have two basic drives for this challenge. One of them is a H drive, one of them is a holonomic drive.
They both perform the exact same function where they can either move forward or straight, side to side, or they have zero turn capabilities. So effectively they can translate across the field while maintaining a forward position.
They're both pretty good at what they do, but the H drive has some advantages the holonomic doesn't. Like the H drive is way better at strafing along side to side. You can have a 5 wide C channel covering your wheels that allows for more support for the side towers or anything you mount on top of the drive. It makes it heavier and a little bit slower, but it doesn't affect the performance as much as it would for a solid tank drive because you have to turn and stuff separately for a tank drive. Holonomic drives, on the other hand, they're really good at pivoting in one point because the wheels are angled, and they're just overall better if you want to move around the field. The holonomic drive would be better in certain challenges like last year with the nothing but net because you can just turn around, pick up a ball real quick and turn back around. It'll also help this year when you pick up a star, turn right back around and drop it across the fence. From a driver's perspective, they both have the same controls.
So the two codes that I have developed are for the holonomic drive and the H drive. The H drive code is quite simpler than the holonomic code. First, we define the variables for each joystick. So Y1 would be for forward movement because that's on a Y-axis if you were recording the robot's movement on a graph. X1 would be for horizontal movement. X2 would just be turning. So what this section of the code does right here is it basically assigns variables a sensor value based on the position of the joystick. So if I want to go forward, then it'll say Y1 would equal the value of that joystick. And at the very bottom we combine all those values and it all accumulates into a final speed of the motor and the final power of the motor, which will determine the direction that it goes. Now the holonomic code uses the exact same principle. We define variables up here. These variables are then incorporated into motor values. And because I have encoders, it let me have the capability to make a self-straightening script so that if it's going forward, it'll automatically adjust, say if there's like a slip on the field or if there's like bumps or something. The way encoders work is they assign a value in rotary motion based on the rotations of a wheel. So using that, I was able to effectively say as long as a robot is not turning, the sensor values for encoders will always be the same if they're diagonal from each other. So once all of that is incorporated, we combine that with the turning variable and bam, you have all of your motor speeds incorporated into one final speed and power.